All right, welcome back to Calculus 2 after our second exam of the semester. So I just have a quick announcement about that. So on some people's exams, for the third question, we talked about the series, I think it was 1 over n squared minus 1. And we asked you to identify what kind of series that is. And it's a telescoping series because you can factor it and use partial fractions. But the correct answer was marked as harmonic series, which it is not a harmonic series. It's only 1 over n. So we modified people's scores based on that. So most people ended up gaining 2 points because most people got that one right. But a few people ended up losing points because they selected harmonic and that wasn't the correct answer. So if your score changed mildly after putting it into the out of 100, that's why that happened. All right, let's see here. I don't think I have any other announcements here. So why don't we just go ahead and get started on the next part of the class. So we learned all about these series, so we can represent functions as these infinitely long polynomials. That's been the goal this entire time. And last lesson, way back a week ago, lesson 24, we started looking at what are called power series, which are these infinitely long polynomials. And the first thing we discussed about them is probably the most important thing, is to check their interval of convergence. So an interval of convergence, if you remember, that's the set of all the x values that you can plug in safely into your series and have it converge. Because there are usually a lot of x values you can plug in that will make it diverge. So we first figure how to do that. Now what we're going to do is we're going to learn how to come up with power series for specific functions. So now that we know how to figure out which x values are safe to plug in, we want to figure out what these series actually are for certain types of functions. So we're going to start doing that today. And so today's lesson is called Power Series Representations. And it's part 1. All right, so last time I think we started off with probably the simplest power series that isn't just something dumb like 0. We started off with this, right? The sum from n equals 0 to infinity of x to the n. And remember, this is 1 plus x squared plus x cubed plus x to the 4th, and on and on and on forever. All right, now we saw that the interval of convergence for this was -1 to 1. So these are the x values that we can go ahead and plug in there. Now, does this series look familiar to anyone? What kind of series does this remind you guys of, maybe? It's the geometric series, right? The only difference is that we just use an x instead of, what did I use before, an r or something? Yeah, so this is like this is a geometric series. So this time we're just only using an x instead of an r here. Now, with a geometric series, we know that if it converged, meaning we were in this range, we actually had a nice formula for what it converged to. So if we start at n equals 0 and we have x to the n, what do you think the formula is for the sum of this series? You guys remember that from last week? What is this? Yeah, so it's going to be this to the 0, which will be 1. And then we have 1 minus x down here. So this is going to be our first power series representation. The sum of x to the n is going to be the function 1 over 1 minus x, provided that we are within -1 to 1. If we go outside of this range, then we're not equal to the function anymore. As kind of an absurd example, let's say we plugged in x equals 2. Then we would get something a bit ridiculous where we have the sum from 0 to infinity of 2 to the n is -1. So the sum of all the powers of 2 are going to end up being -1 here. So if I plug 2 in for this, this is 1 over 1 minus 2. So this is why we need to stick with our interval of convergence, because otherwise we get absurd results like this right here. So we need to stick within our interval of convergence. All right, now what we're going to do is we're going to use what's called the substitution method to get more power series besides this one, because this is only just one function, right? but we can end up getting a lot more functions by manipulating this one. So for my first example, let's say I want to find a power series representation for f of x is 1 over 1 plus 2x. All right, so what we're going to do, how we're going to get representations of functions that look like this, is we're going to imagine our geometric series being written like this. We have something, or a blank, to the n is 1 over 1 minus blank. So what we're going to do is we're going to try to manipulate this algebraically to be 1 over 1 minus something. And once we're able to do that, then our series will just be whatever that something is to the n. And furthermore, the interval of convergence is always going to be whatever we put in here. So whatever's in that blank space, the absolute value of that needs to be less than 1. So let's go ahead and try this. This is very important. So let's box that. So let's go ahead and try this for 1 over 1 plus 2x. Now let's see here. We're actually already almost in this format here, right? So we have a 1 on the top. That's okay. We have a 1 right here. That's okay. But the thing is, we have a plus instead of a minus right here. Will all those blanks be the same value? Yeah, this, and this are all the same thing. That's right. So we need to get this to be 1 over 1 minus something. So how can I rewrite this so this will be a minus right here? Yeah, we can factor out a negative. That's right. So every positive we have can be written as a negative negative. So this is the same thing as saying 1 over 1 minus negative 2x. Now, we now perfectly have it in this form. It's 1 over 1 minus something, right? So the thing that's going to go into our blank is negative 2x. So this is going to be the sum from n equals 0 to infinity of negative 2x to the n right here. So this is going to be our power series for 1 over 1 plus 2x. Now, we could leave it like this. This isn't wrong as it's written, but it's better for stuff we're going to do later to distribute the n over the minus, the 2, and the x. So if I distribute an nth power to a minus, that's just like saying negative 1 to the n. If I distribute the nth power to the 2, that's 2 to the n. I distribute the nth power to the x, and I have x to the n. So this would be the preferred form for this power series right here. So there we go. We did it. We found a power series for a different function here. Now, whenever we find a power series, just as important as finding the formula is finding the interval of convergence. Because remember, only having the formula isn't that great because we don't know what x values we can plug in. And if we plug in an x value we like, it might end up diverging. What about the absolute value less than 1? Yeah, that's what I'm getting to right now. So the interval of convergence comes from this. So whatever we put into our blank space, which in this problem was negative 2x, it needs to be less than 1. Now, any negative inside an absolute value will just go away, and I can move the 2 out. So we have 2 absolute value of x is less than 1. Absolute value of x is less than 1/2. And then if I get rid of the absolute value here, I have x's in between negative 1/2 and 1/2. So using my old interval of convergence right here, I was able to create my new interval of convergence. So there we go. So we found the interval of convergence. We found the series formula. So we're done here. We now know a series representation for 1 over 1 plus 2x. We can write that as one of those infinitely long polynomials if we so desire. All right, now I want you guys to try something very similar. It's time for a practice. So I want you to find a power series representation for 5 over 1 plus x squared. And then also find the interval of convergence and the radius of convergence as well. All right, so go ahead and try that for a bit. Do we not plug in the 1/2? We don't need to here because since the geometric series didn't include its endpoints, this won't include its endpoints either. So we don't need to plug in a half, a negative a half, if it comes from the geometric series. But it's good that you're thinking about endpoints, though. Those will be important later. Are you allowed to pull out the 5? Yeah, sure. No issue with that. The powers get raised to the nth power too? Yeah, that's right. Well, don't forget your power rules. So if you raise a power to a power, that's multiplying powers. All right, maybe another minute or so, and then we can go over this one. All right, let's go ahead and try this one out. So we want to find a power series representation for 5 over 1 plus x squared. Now, our goal is to get it to look like this, 1 over 1 minus something. Because if we can get it to be 1 over 1 minus something, we know that the power series for that is just whatever that something is to the n. And we also know the interval of convergence too. So let's see if we can use algebra to get it to be like 1 over 1 minus something. All right. So we start with our 5 over 1 plus x squared. Now let's see here. I have a 5 on top, but I really want a 1. So I guess I can factor a 5 out of that. So I can kind of just leave my 5 out there. Then I have 1 over 1. Okay, that's good. But then this needs to be a minus right here. But how did we deal with the plus sign before? We just wrote it as the negative of a negative. So this will be 1 over 1 minus negative x squared, like that. All right, and then finally we have it as 1 over 1 minus something. So that something is going to be raised to our nth power. So we have 5, and then we have the sum from 0 to infinity of negative x squared to the n. Now, just like before, it's going to be desirable in the future, actually in the near future, to have the x on its own, not attached to anything like this negative right here. So I do negative to the n is going to be negative 1 to the n. And then I have x squared to the n. Now, if I do a power to a power, I just multiply those powers together. So what does this end up being? This ends up being 5 times the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n. So if I were to write out this infinitely long polynomial, all of my terms would be even. So I'd have a constant, then x squared, x to the 4th, x to the 6th. So no odd powers of x will be here. And then finally, we also want to know the IOC and I guess also the ROC. So remember, for finding the interval of convergence, we take whatever we put in our blank space and we put it in here. So we have negative x squared, and absolute values is less than 1. Now let's see here. Absolute values will get rid of any negatives that we have. But then once we get rid of the negative, the thing inside the absolute value is x squared. Now x squared will always be positive. So once the absolute values get rid of the negatives, we can leave them safely behind because we know this will always be positive. So this is the same thing as saying that x squared is less than 1. Now, if I don't know if you guys remember this from algebra or not, but how do we deal with an inequality that has a square in it? Well, what we do is we take the square root of this number, put its negative over here, and then we can get rid of the square. So the square root of 1 is 1. I put a negative on 1. I put it over here, and then I can get rid of my square. So my interval of convergence will be from negative 1 to 1, meaning that my radius of convergence will be 1 right here. All right, so that was another example on how we found a power series representation. Do we not have to multiply by 5? Yeah, that's a good question. So the 5 wasn't the thing that we put inside the blank, right? The 5 is just a constant that we have out here. So the 5 doesn't really have anything to do with the interval of convergence. And is it negative 1 to 1 with parentheses? Yeah, that's right. All right, so let's move on to another example. So in both of the previous examples, we had that 1 on the bottom already there. So we didn't need to worry about that. But what happens if we don't have that? So this time, our function is going to be, what did I write here? X squared over 2 minus x cubed. And I want to find the power series representation, the IOC, and the ROC. Okay. So let's see here. Remember, my goal is to get this to be 1 over 1 minus something, because I know how to turn that into a series. Now, I can get a 1 up top the same way I got it the previous time. I could just factor out an x squared here. And yeah, you could even do that if it's a variable. It's okay that that wasn't just a number. We could actually factor out variables as well. So we can factor out an x squared right there. Now on the bottom, I guess we could apply the same reasoning and we could factor out a 2. So we pull out a 2 from the bottom. We have 1 over 1 minus. Now, if I pulled a 2 out from the entire bottom, that means that this x cubed now needs to be divided by 2. So this is now an x cubed over 2. So watch out for that if you're factoring out something from the bottom right there. And you can see that this is the same as this if you multiply back through. We have 2 times 1 is 2, and then the 2 will cancel with the 1/2 there to give us our negative x cubed over 3. All right, now if you look carefully here, we actually already have what we want. We have 1 over 1 minus something. So what we're going to have is we're going to have x squared over 2, and then we have the sum from 0 to infinity of x cubed over 2 to the nth power. All right, now I'm going to do 2 things to clean this up. I'm going to distribute the n just like I have for every other one of these. So I have x cubed to the n, that's x to the 3n. And then I have 2 to the n. Okay. Now, usually with power series, we want all of our x's, and if possible, our constants, all in the same place. So what I could do is if I multiply in this x squared here, and I combine it with these x's, then what power of x will I end up having in my numerator? It'll be x to the what? Yeah, it's going to be 2 plus 3n. That's right, 3n plus 2. Because we have x squared times x to the 3n. We add the exponents together and have x to the 3n plus 2. All right, and then we can actually do the same thing with the bottom as well. So this is technically 2 to the 1 times 2 to the n. So that means that'll be 2 to the n plus 1. So we can get this in an even more compact form than we had it right here. And this is definitely more desirable than this is right here, for reasons we'll see in the next example. All right, now it's not enough to just find the formula for your power series. We also need to find the interval and radius of convergence as well, so we know which x values are okay to plug into our series. So the thing that we put into our blank space was x cubed over 2. So the absolute value of x cubed over 2 needs to be less than 1. Well, let's see here. If I multiply both sides by 2 here, I have absolute value of x cubed is less than 2. All right, now the thing with cubed roots and odd roots and inequalities is you could just take that root of both sides and not worry about it. So I'm just going to take the cube root of both sides. And I end up with the cube root of 2. And then finally, in order to get rid of our absolute value here, I can get rid of it if I'm willing to put a negative copy of this on the other side. So I have negative the cube root of 2, x, and then the cube root of 2. So these are all of the x values that are okay to plug into my series. And what's the radius of convergence? It's going to be the cube root of 2. It's going to be half the length of this interval here. All right, so that's about as tricky as it gets with this. Sometimes you have some weird number that's not 1 or something that's not 1 right here. You can just factor that out and then do the same procedure that we've been doing earlier. All right, so now this isn't the only way of getting power series. Otherwise, this would be kind of limited, right? We can only really get power series of things that look like 1 over 1 minus something, and that's not too many functions. So what we're going to do now is we're going to expand our horizons and find a different way of coming up with different power series. By the way, so some of you may have been wondering about this absolute convergence thing, right? Like that kind of just seemed like some extra thing that we just tacked on to make things worse. You know, what's the significance of absolute convergence? You can only do the substitution method if your series is going to be absolutely convergent. So that's kind of in the scenes. So can only, or behind the scenes. So that can only use this method on absolutely convergent series. Now, the good thing about this is that within our interval of convergence, like if you look in the middle of the interval of convergence, if it converges, it's always going to be absolutely convergent. So we don't need to manually check for absolute convergence. It's just going to be there when we need it. But that's kind of what's going on. And that's why absolute convergence is significant. It's also going to be significant for the next way we're going to find series. So let's look at our next example, example 3, right here. Let's see. Let's find the power series representation of f of x is natural log of 1 plus x. And then we also want to know the IOC and the ROC too. Okay, now if we look at this, I think it's pretty clear that we can't do the 1 over 1 minus something trick with this right here, because it's a natural log. And that's significantly different from the type of function that we had before. Now, the nice thing about infinite series or power series is that you could treat them like infinitely large polynomials. And one thing that's really easy to do with polynomials is to integrate them. How do we integrate a polynomial? We just bump up the power by 1 and divide by the new power. So the same thing goes with power series as well. And this is starting to be this is going to be the first main advantage that we see with power series here. It's really easy to integrate them. So let's see here. I know that if I had the series for 1 over 1 plus x, and I integrated this, that would integrate into ln of 1 plus x, right? So if I find the series for this, and integrate, that will get me to the series for ln of 1 plus x right here. And I technically should put absolute values here, but we'll see that the interval of convergence will make it so this isn't negative. All right, so first I'm going to find the series for this, and then I'm going to integrate. So let's see. 1 over 1 plus x, it's already almost all the way to being in the form where we could just substitute. The only difference is we have a plus here instead of a minus. So let's make this 1 over 1 minus negative x. Now, once we do that, this is the sum from n equals 0 to infinity of negative x to the n. Now, if I apply the nth power, we have negative 1 to the n, x to the n. So this is going to be my series for 1 over 1 plus x. And I could find the interval of convergence as well. The thing I substituted in was negative x, so I have absolute value of negative x is less than 1. But that's just the same thing as absolute value of x being less than 1. Or x going from negative 1 to 1. Okay, so we found the power series and the interval of convergence for this. Now let's go ahead and integrate everything. So what I'm going to do is I'm effectively integrating both sides of this equation. So the integral of 1 over 1 plus x by design is what we want. ln of 1 plus x. Then I guess we should do a plus c, since we did an integral. And then over here, I'm going to do the integral. Well, actually, I'll have the plus c on the other side. Now, what I'm doing is I'm doing the integral from n equals 0 to infinity of negative 1 to the n, x to the n. Now, how are we going to do this? How are we going to do an integral of a series? How does that even make sense? Well, remember, a series is just addition, right? And we had no problem earlier splitting our integrals over addition. So for example, if we want to do the integral of x squared plus x cubed, we just do the integral of each of those separately and then just add them together. So what that amounts to here is that we could just move our integral inside the sigma, because this is just a bunch of addition, and integrals can split over addition. Okay. Now, I want you guys to pay attention here. This is an integral with respect to x, right? X is the variable that we're looking at here. More specifically, n is not the variable that we're looking at for the integral, meaning that n counts as a constant. So this negative 1 to the n right here, this is just some fixed number. And when we have a fixed constant, we can just move that out of our integral. So this is the sum from n equals 0 to infinity of negative 1 to the n, and then we have the integral of x to the n dx. All right, and then now we're just doing the integral of a polynomial. We raise this power by 1 to be n plus 1, and then we divide by the new power. So let's recap. We have ln of 1 plus x, and then when we do this integral, we have negative 1 to the n, x to the n plus 1, and then I divide by my new power, which is n plus 1. And then we could put in a plus c now that we finished the integral here. So this is one of the primary advantages of using power series, is that it's really easy to integrate the functions. Now, granted, integrating 1 over 1 plus x was also not difficult. But on the other hand, if you have something over here that's like really difficult to integrate, like say sine of x squared, rather than integrating this directly, you could instead integrate its power series, which will always be easy to do. So this is one of the first advantages and one of the reasons why we write things as power series. All right, now we have this plus c here. We can figure out what that is by plugging in x equals 0. So if I plug in x equals 0 on this side, I have ln of 1, which is 0. Now, what happens if I plug in 0 into the series? What is the series going to end up giving? I'll plug in 0 for x is 0. It's just all 0, right? Because we just have 0 to a power and then times all that other stuff. So we have 0 is 0 plus c. Well, that means that c will be 0 as well. So we don't need to worry about that constant here. All right. I missed derivatives? Yeah, we'll be having some of that later too. All right. So we have ln of 1 plus x is this series right here. So we found our series for ln of 1 plus x. But why did we plug in 0? So we can figure out what the constant is. And since I know what ln of 1 is easily, that's why I plugged in. X is 0 right here. All right. So now I have the series. So the series is one thing, but I also need the interval of convergence. Oh, yeah, what's up? So like take the derivative. So you're saying take the derivative of this and get its series and then integrate? Yeah, that's effectively what we did here, because I kind of imagined that the derivative of this was that, and then I found the series. Yeah, so you can do it that way as well. So yeah, what the audience is saying is that you can take the derivative of this, find out what function it is, and then you find the series for that and integrate it. And that's kind of a different way of viewing this process here. All right, but getting a series formula is only as good as our interval of convergence, because we need to know what x values we plug in. Now, the nice thing about integrating a power series is that the interval of convergence is mostly the same. So let me write out how we're going to do this. When integrating to get a power series rep, the IOC will be the same as before, except we might add the endpoints. All right, so what does that mean? Well, remember that the interval of convergence for the thing that we had before was -1 to 1, but we didn't include the endpoints, right? It was strictly in between -1 and 1. But now that we've integrated, it'll still be -1, 1, but there's a chance that we could now include the endpoints here. So what we need to do is we need to check the endpoints to see if they ended up being included when we did the integration. So let's check x is -1 into our new series. So we have -1 to the n, -1 to the n plus 1 over n plus 1. Let's see if this converges. Well, we have the sum n equals 0 to infinity. Now, I have the same base here, so I can add the powers together. N plus n is 2n, and then I have plus 1. Okay, now let's take a look at this. 2n plus 1 is a what type of number? It's always an odd number. That's right. Now, if I raise -1 to an odd power, like -1 to the first, -1 cubed, -1 to the fifth, what am I going to get for all of those? It's going to be negative for all of them, right? No matter what odd number it's going to be. So this is just a fancy way of writing -1. So this is just negative the sum from n equals 0 to infinity of 1 over n plus 1. All right, and then what is this series going to do? Is this going to converge or is this going to diverge as a series? Yeah, this is going to diverge, right? Because it looks an awful lot like the harmonic series. Because if we plug in 0 here, we have 1 over 1 is 1. We plug in 1 here, we have 1 over 2. Plug 2 in here, we have 1 over 3. Actually, this is the harmonic series. It's just written a little bit different. So this is going to diverge because it's the harmonic series and it fails the p-test. So we're not going to include -1. So notice that the key word for this rule is might. So we don't need to add an endpoint. It's just possible that we could. Now let's check out what 1's going to be. Maybe we'll add that one. So I have n equals 0 to infinity, -1 to the n, 1 to the n plus 1 over n plus 1. Okay, now 1 raised to a power will just be 1, right? So, and multiplying by 1, we don't even need to write that. So this is -1 to the n over n plus 1. Okay, now what is this going to do as a series? Is it going to diverge like the other one, or is this going to converge this time? It's going to converge this time. That's right. And this time, it's going to converge by the alternating series test. Because this is an alternating series, it's decreasing and heading to 0. So this is going to converge by the alternating series test. So while we wouldn't include -1 as a bound, we would include 1. So we added the endpoint 1 into this. What happens to the -1 to the 2n? Are you talking about the previous one here? The -1 to any odd power is going to be negative. All right, so this is our interval of convergence. And notice that the radius of convergence is still going to be 1. One interesting thing about integrating is that integrating never changes the radius of convergence. So integrating keeps the ROC the same. And it makes sense if you think about it, because you're still going to have the same endpoints. So the distance between these will be the same as before, and then dividing that by 2 will be the same. So the radius of convergence will always just be the same as whatever the original one was. That will never change. Whereas the endpoints may change by a little bit right here. All right, so why don't you guys give this a shot? So remember that we had as an answer from earlier, remember our series from before. What was our series from before, from the previous example that we did? We have 5 times the sum from n equals 0 to infinity of -1 to the n, x to the 2n is 5 over 1 plus x squared. So I want you to use this to find the series for 5 arctan of x. And also the IOC and ROC. And remember, our original IOC for this was -1 to 1. So we could end up adding these endpoints right here. All right. So yeah, go ahead and give this a shot. Why did we do -1 and 1? The endpoints of our original IOC was -1 to 1, the one we had before the integral. So when we do the integral, it's still going to be something from -1 to 1, but we might end up including -1 or 1. So we need to put those into the series manually. So we need to plug it in directly for that x and see if it converges. And as with this example, we actually did end up including 1, whereas we didn't before. Use brackets for when it's less than or equal to, yeah, that's right. And then you use parentheses when you don't include it, or it's just strict less than or greater than. Give you guys one more minute, and then we'll go over this one and then do one more example. All right, let's take a look at this. So we want to find the series for 5 arctan of x. And I already wrote down that we know the series for 5 over 1 plus x squared. So conveniently, it turns out that the integral of 5 over 1 plus x squared is arctangent of x. So what we're going to do is we're going to integrate both sides of this equation here. So I'm going to do the integral of 5 over 1 plus x squared. And I'm going to do the integral of 5 times the sum from 0 to infinity, -1 to the nx to the 2n. All right, now as I just said, this is going to end up being 5 arctan of x. Now here, just like the other time we did an integral, we can ignore this because it's a constant. We can go through this because it's addition. We could go through this because it's another constant with respect to x. So what all we're doing here is we're just integrating x to the 2n. That's all that we're really doing with this integral. It looks really complicated here, but then once we get to here, all we're doing is just the power rule here. So if I do the power rule on x to the 2n here, what will I get? What will I get if I do the power rule on x to the 2n? Yeah, I'm going to get x to the 2n plus 1, so I bumped it up by 1. And then I divide by my new power. So I divide by 2n plus 1 here. And then we have plus c, because we did an integral. All right, but now I could plug in x equals 0 into here, because arctan of 0 is a convenient number. It's 0. And then if I plug 0 into the series, 0 to any power will be 0. So we end up with c is 0 right here. So this is going to end up being our series. All right, and then we need to find the interval and radius of convergence. So most of that work is done for us. The interval of convergence will definitely be from -1 to 1, but we need to know if we're going to include the endpoints. So if I plug in x equals -1, I'm going to have 5 times the sum of -1 to the n, -1 to the 2n plus 1 over 2n plus 1. Now we talked about this earlier. -1 to the 2n plus 1, that's just a negative. Negative to any odd power will be negative. So this is just a negative, so I can move it out as a constant. And then I have -1 to the n over 2n plus 1. So is this one going to converge or diverge as a series? It's going to converge by the AST. So we're actually going to include -1 this time. And how about x equals 1? What about that? Well, let's see. I have -1 to the n, 1 to the 2n plus 1 over 2n plus 1. All right, so with here, 1 to the 2n plus 1, I can get rid of that, and I have -1 to the n over 2n plus 1 right here. And that's going to also converge by the AST right here. So we're actually going to include both of our endpoints when we integrate it here. All right. Finally, I bet you could probably have guessed that this was going to happen. So if the endpoints converge, we keep them. That's right, because the whole point of the interval of convergence is to identify which numbers we could plug into the series and have them converge. So that's kind of the whole point of doing that. All right, and then for my final example here, I want to find the power series rep for 1 over x squared. And this time, we're actually going to use differentiation to get this. So what I'm going to do is first, I'm going to find a series for 1 over x. And why would I find a series for 1 over x? Well, if I take the derivative of 1 over x, I can get to, well, at least pretty close to 1 over x squared. We need to multiply by a negative here, but that will still get me there. All right, so what am I going to do? Well, let's find a series for this. Well, for this is missing the 1 down there, right? So I want to write this as 1 over 1 minus something. So I can use my series from earlier. Now, what I could do is I could put in a 1 here, and that way these 1s will cancel out. And then I could put a negative x in there, because if I do a negative times a negative, I'll have the positive x that I want. right here. All right. So then now that I have this, I know this is going to be the series n equals 0 to infinity of 1 minus x to the n. Now, we usually like to have it where x doesn't have a negative on it. So I'm going to flip the order of this, but that will gain me a negative side. So I have negative x minus 1 to the n, but then having a negative to an n is negative 1 to the n. Okay. Now let's see. So this is my series for this right here. And let's get the IOC while we're at it. Whatever I put into my blank space, which was 1 minus x, absolute value of that needs to be less than 1. So if I use the absolute value rule here, I could put a negative 1 and get rid of that. And then I'm going to subtract 1. And then I'm going to multiply by negative 1. But remember, when we multiply an inequality by a negative, all of the inequalities flip. So my interval of convergence here will be from 0 to 2. So that's a bit different from what we're used to seeing here. All right. Now let's go ahead and take the derivative of this. So I'm going to do the derivative of 1 over x, which can also be written in the series form. All right, so the derivative of 1 over x is negative 1 over x squared. And now if I do the derivative of a series, you would kind of like the way it worked for integrals, the same thing works for derivatives. We ignore the sum because derivatives can go over sums. We ignore the constant here, and we just take the derivative of this. So we have n equals 0 to infinity, negative 1 to the n, and then we have n x minus 1 to the n minus 1 right here. Why do I use 1 over x and not 1 over x squared? Yeah, you might be thinking, oh, I could have cut out the middleman here and just made this be a square and then use the 1 over 1 minus thing for that. I'll explain that at the end why I didn't do that. Now, there's one little caveat here. So we don't need to worry about plus c's for differentiating. But there is one little issue. If I have n equals 0 and I put that into here, this will be x minus 1 to the negative 1, right? So that'll be 1 over x minus 1. And that's not a polynomial. So what are we supposed to do? Well, the good news is that n equals 0, it'll kind of zero it out here. But since that term is going to be 0 anyways, we start our series one term later. Because we can just chop off that 0 term. And then our series is properly a power series. We don't have 1 over something here. All right, so we need to change our index. And if we did another derivative, say, we would need to bump this up 1 more again to be n equals 2. Now, finally, all I need to do is just multiply both sides by negative 1, and I have what I want. So this is going to be my series for 1 over x squared here. And for the interval of convergence, let me explain how this works for derivatives, and then we'll be finished here. So when differentiating to get a power series, the IOC will be the same as before, except we might lose endpoints. So our original IOC for this, before the derivative, was 0 to 2, right? So that means that after we do our derivative, the endpoints will still be 0 and 2, although if we had any endpoints before, we could potentially lose them. But the thing is, we didn't even include the endpoints in the original one, right? So we don't have any endpoints to lose, and we can't gain them. Remember, this isn't an integral. We can only lose endpoints when we do a derivative. So since we don't have any endpoints to lose, we're still going to have this as an interval. Now, maybe if we included, like, say, the 0 before or something, then we would have to test that here to see if it's still going to be there. But since we didn't have it to begin with, and derivatives can only take away endpoints, then this is going to be our new IOC. Now, finally, one more thing. I know I'm over time here. Oh, I'm sorry. Yeah, one thing real quick. I want to explain why I didn't just do 1/1 minus 1 minus x squared. If I would have done that earlier, so if I would have done this earlier and skipped out on all this derivative stuff, then the series I would have ended up with is this right here. And while this isn't wrong, there isn't anything technically wrong with this, it's not useful. Because if we wanted to do the derivative or integral of this, we would have to use a use substitution with this right here, because it isn't just an x. And that's why I wanted you guys to always get things to be just x to the n, so we don't have to think about that. But because we have 1 minus x squared, and that's raised to the n, we no longer get easy derivatives and integrals. And furthermore, all the things we're going to learn about power series later don't apply to ones that look like this. So that's why we didn't want to do it this way. It's not wrong for this inequality right here. It's just this is useless. So we don't want to do it. All right. Anyways, that's it for today. Oh, yeah, I forgot to mention. Yeah, so Wednesday is recharge day, so there's no class on that day. So I guess I will see you guys on Friday, where we will continue learning about power series.